Hello everyone, welcome to Module 2. In this session, we'll dive into something really exciting, goal-based problem solving. We all solve problems every day, right? Like building a Lego set, figuring out a tricky puzzle, or even deciding what to wear when it's raining. Today, we'll learn the smart way of doing that by setting a goal and then taking steps to reach it. We'll even use a model building activity to understand how to think like a little AI scientist. Before we start something new, let's quickly remember what we learned before. In Module 1, we talked about two kinds of problem solvers: biological agents, that's us humans, and AI agents, that's machines and robots. We humans use our brains, memory, and senses to understand the world. We can see, hear, smell, taste, and touch to gather information. Then we use that information to think and take action. Now, AI systems use something similar. Sensors act like their eyes, ears, data acts like their experience, and algorithms their brains. And their actuators help them do things like robotic arms or wheels. Question for you. Can you name an AI system you have seen that can sense and act? Now, let's move forward. Perfect. So you will keep that connection in mind as we explore problem solving today. Let's look at what we'll be doing in this module. By the end, you will be able to solve a problem with goals and plans, learn about problem-solving environments, understand what supervised learning means, use ideas like decomposition and abstraction, know the difference between strategic and tactical planning, and most importantly, you will learn how to plan, decide, act, and evaluate your solution just like an AI agent. Did you know that people have been teaching computers to solve problems since 1960s? Two scientists, Newell and Simon, used a method called means end analysis, or MEA in short. It was used in something called GPS problem solver. Don't worry, not the one on your phone. The MEA method works like this. You start from an initial state, your starting point. You have a goal state, your target or final result. You always check your present state, where you are right now, and at each step you see how far or how close you are to your goal. That's called symbolic distance. So the idea is to take small, clever steps that bring you closer and closer to your goal. It's a lot like solving a maze or building with blocks. Here's a colorful cartoon to help us see all those parts of MEA in action. You will notice the initial state, where the character begins, numbered 1. Then the goal state, where they want to reach, and the present state, what they are doing right now. And each action they take makes the distance smaller and smaller to the goal. The key idea: every good problem solver keeps the goal in sight and moves closer to it every step. This strategy was applied in 1960s in the GPS problem solver by early AI scientists Newell and Simon, the era known as symbolic AI or good old-fashioned AI. In this slide, we will watch the cartoon's explanations for each of these MES steps.
Hey Jesse, have you ever thought about how playing basketball is a bit like solving a puzzle?
What do you mean?
Well, think about it. Before the game even starts, we're at what we call the initial state. Everything is set up, but no plays have been made yet.
So the initial state is like our starting point when we step onto the court?
Exactly. And then our goal state is winning the game by scoring points.
Okay, so if the initial state is the start of the game and the goal state is winning, what exactly is the present state?
Great question. The present state is where we are right now in the game. It shows our current progress and helps us decide what to do next.
So if our team is a bit behind, knowing our present state tells us we need to adjust our plays to get closer to our goal state?
Exactly. It's like taking a quick look at the scoreboard to see how far we've come and what steps we need to take. Now, let's talk about symbolic distance. Imagine it as the gap between where we are right now, the present state, and where we want to be, the goal state.
Kind of like the distance on the court between us and the basket when we're setting up a play?
Exactly. That distance represents the effort and strategy needed to bridge the gap. Sometimes it's a long way, meaning there's a lot to work on, and sometimes it's just a short sprint.
So, by understanding the symbolic distance, we can figure out the steps needed to move closer to winning the game.
Right on. It's all about planning the right moves to close that gap efficiently.
So, if I understand correctly, our strategy involves knowing where we started, understanding our current situation, and keeping our eyes on where we want to be, while always considering the gap we need to cover.
That's exactly it. By analyzing our initial state, present state, goal state, and the symbolic distance between them, we can plan and adjust our plays effectively throughout the game.
It's like having a clear roadmap for success, not just in basketball, but in any challenge we face.
Absolutely, Jesse. When we know our starting point, our current position, and our destination, we can make smart moves and work together to achieve our goal.
Now we are going to experience problem solving with our building blocks. There are 8 steps in this whole process. First, identify the problem, define the problem, explore the problem, learn about it, plan, make decisions, act, and evaluate your results. When you finish step 8, which is evaluation, guess what? If you still didn't reach your goal, we loop back. We repeat the process until you reach your goal. That's what problem solving is all about. So we begin our goal-based building block activity. The intention is to learn about the 8-step problem-solving process using building blocks. Now that we have all the blocks in front of us and the picture of the model to build, let's start. Let's start with step 1, identify the problem. In our building block activity, the problem is choosing which model we will build. You will see 2 designs, style E and style F. So ask yourself, which one do I want to make? That's your goal. Once you choose your model, you have identified your problem to solve. Next is step 2, define the problem. This means understanding what kind of problem it is. We ask questions like, do I know everything I need? Whether it is a known or an unknown environment. Can I see everything I need to build? Fully or partially observable environment. Does anything change while I build? Is it a static or a dynamic environment? Am I building alone or with a partner? Is it a single agent or a multi-agent environment? These help us know exactly what kind of environment the problem exists in. Just like AI systems think about the type of world they are working in. Let's take a look at these fun cartoons that explain problem-solving environments. They show us examples of known versus unknown. Do we already know all the steps or not? Fully or partially observable. Can we see everything or only part of it? Single or multi-agent? Are we working alone or with others? For example, playing chess is fully observable and two-agent, but building blindfolded would be partially observable. That's a tougher problem to solve. Let's watch the videos.
Some mazes are familiar to us, like the paper maze we solved last week. That's what we call a known environment.
Exactly, because we've seen it before and we know some of the tricks to navigate it.
But sometimes we face a maze that is completely new, an unknown environment, where we have to figure everything out as we go.
Just like when the robot first encountered its maze, it had to learn the layout from scratch. When every part of the maze is clearly visible, we say it's fully observable.
That's like our paper maze, where we could see every turn and pathway clearly.
But sometimes, parts of the maze are hidden or hard to see. That's called a partially observable environment.
Just like when the mouse or the robot encountered unexpected corners where the full path wasn't immediately clear.
Remember how the little mouse navigated its maze all on its own? That's an example of a single agent environment.
Right, and the robot that used its sensors to solve the maze was also working as a single agent.
But when we team up to solve our paper maze, we become multiple agents, combining our ideas and strategies to find the best pair.
Exactly. It shows that sometimes having more than one agent working together can lead to smarter solutions.
Now, let me explain what a static versus dynamic environment is. You remember you solved the simple paper maze. That was a static environment. While the mechanical maze that moved with moving the gears was an example of a dynamic environment. Now we move to step 3, explore the problem. This means gathering everything you need and learning what you have. So go ahead, spread your building blocks on the table. Now ask, which blocks will I use? How many of each? Here, we'll also learn 2 types of moves. Episodic moves, order doesn't matter, like sorting colors. Sequential moves, order does matter, like stacking specific shapes. In many problems, AI needs to know which kind of moves it can make. Let's watch the explanation again.
Finally, let's explore sequential versus episodic environments.
In a sequential environment, every move you make influences the next, like following a continuous path through a maze.
That's just like our paper maze, where each decision leads directly to the next step.
In contrast, an episodic environment is made up of separate challenges. Each decision is more isolated, like individual episodes. Understanding these differences helps us see how different environments shape the way we solve problems in AI tasks.
Let's learn about the problem now. In this step, we study the instructions and the pictures closely to really understand what we need to do. It's like training your brain before you start building, learning from examples so you can avoid mistakes later. Now comes strategic planning. Think of it as a big picture thinking. Before you start building, visualize what your final model should look like. Decide how to get there. We'll plan for a problem environment that is static, fully observable, and mostly single agent. Think about your overall plan first before you begin. That's strategic thinking. Let's hear out the cartoons.
All right, Commander Jake, mission briefing time. We've got the blueprint for the ultimate rescue truck.
Captain Lila, confirm? We have a fully observable, known, and static environment. No sneaky surprise blocks.
Totally, all the pieces and instructions are right here. So what's the strategy?
Strategic planning first. We decide the big picture. Let's build submodels: base, cabin, wheels, and lights.
Now let's zoom in on the small steps. This is called tactical planning. When we break the model into smaller submodels, that's decomposition. When we focus on the important parts and ignore what doesn't matter, that's abstraction. Ask yourself, can I build the smaller sections first? Can I change the order? Let's watch this video to see what the cartoon says about each.
Now comes tactical planning. We break down each submodel. That's called decomposition, right?
Exactly. And abstraction means we don't worry about every brick. Just carefully select the blocks that match the shape for each submodel they go with.
Let's start with the wheels. They're the simplest. Build confidence first. Then we tackle the trickier cabin.
Step 1. Let's select the easiest submodel. It is E5 and keep aside the 4 wheels. Easy peasy. We could select any of the submodels. The order does not matter. Such moves are called episodic.
On the other hand, to construct the submodel, connect each block in the order shown in the instruction. These moves are called sequential moves as it is required to connect the blocks in a particular order, or it may not match the picture in the instruction.
Well, now that we have understood what tactical planning, decomposition, and abstraction is, let's look at a demonstration of decomposition and abstraction in the context of building blocks. Here's why tactical planning is super important. It helps you do things right the first time. When we think ahead, we avoid repeating mistakes. Let's watch the short clip that shows what happens when people don't plan. Compare it with what good planning looks like. After that, we'll talk about what we noticed.
Cabin's more complex, lots of tiny pieces.
Yeah, and some bricks go under others. Gotta follow the sequence exactly, or the roof won't fit.
This is why tactics matter. One misstep, and we're rebuilding the submodel from scratch.
Okay, it's time to act. This is step 7. Start building your model carefully, just the way you planned. Now, after building each step, evaluate. That is step 8. Once you finish, look closely. Does it look like the picture? If not, that's okay. Adjust your steps and try again. This final check help us remember. Remember, real problem solvers always test and improve.
All submodels ready. Time for the big merge.
Like fitting puzzle pieces. Let's go from bottom up. Base, wheels, then cabin.
And ta-da! One rescue truck powered by planning.
Let's connect what we did up to now to how AI learns. When you followed the pictures and instructions, they acted like training data for you. The labeled pictures E1, E2, F1, F2 told you what each part should look like. Those were your labels. By studying them, you trained yourself to build correctly. That's what AI does in supervised learning.
Let's take a quick review of all the new ideas we learned today. Strategic planning, tactical planning, decomposition, abstraction, sequential versus episodic moves, means end analysis, problem solving strategy, and the 8-step problem solving process. So, now share a real life example of how you have used these ideas or steps. Let's apply this to real life. Imagine your goal is to reach school on time, that is, before 8 a.m. That's your main goal, the big picture. Now, what smaller things do you have to do first? You might say wake up, brush your teeth, get dressed, have breakfast, pack your bag, and leave the house. Those smaller activities are your sub goals. That's decomposition. Now think, how much time do you need for each one so you reach school on time? That's tactical planning. Now complete the timings for each of these steps in the chart given below. Before we finish, we'd love to hear what you thought. What did you enjoy the most? Which activity helped you understand planning better? Think about which step you might use in everyday life, maybe for a school project, game, or even a family task. Now let's play a quick Kahoot quiz to test what you have learned. Grab your device, type in the game code, and let's see who remembers the 8 steps of problem solving. Are you ready? Let's go. Now this Kahoot activity is only available to in-person classes.